Hey everybody, it's Mr. Gopal here with another physics lesson from the Modern Physics Unit. Specifically, I want to talk about Bohr's model of the atom. Now, if you think about it, we've already talked a little bit in previous videos about the idea of this kind of photon effect and the energy levels of electrons. And so if electrons are energized, they can be moved to energy levels farther out from the nucleus. But in that state, they're unstable because we have electron configurations for every atom. And so they can't exist there forever. When they fall back down, they release that energy that they absorbed in jumping outwards, and that comes out in the form of light. And so we have this photoelectric effect happening when electrons return to stability. Before we dive into some of the really nitty-gritty stuff of modern physics, we need to pad our background. And this comes in part from revisiting concepts that were covered in chemistry. So we know, first of all, that the atom has undergone many iterations in its modeling. All right. When we say the atom, we're talking about the smallest unit of matter that has all of the characteristics of matter. So a single atom can be composed of protons, neutrons, and then orbiting electrons. All right. And this is the basic model that we use at the high school chemistry level. However, there were models before it. So for example, we have Democritus, who first came up with the idea of the atomic model, atomos being the Greek word for indivisible. Then we have Dalton, who said that the atom was shaped like a hard sphere, but he gave no detail to the contents inside. What we're interested in today are the contributions of two scientists much farther down the road, specifically Ernest Rutherford and Niels Bohr. And what we want to look at first is the gold foil experiment, because this is where we start to develop a reason, an experimental outcome that helps us, I guess, arrive at the model of the atom that we end up using today. All right. And so in the gold foil experiment, Rutherford was able to set up what we call an alpha particle emitter and fire it at gold foil. And so the idea about the atom at that point was that atoms were bound close together in objects, all right? So if I take my phone, for example, it is thick with atoms, all right, and there is barely any space between them. So what he predicted was he was firing alpha particles, which are positively charged particles, and because we know that, or he felt that atoms were probably positively charged, that they would bounce off, all right? They would be repelled because we know now from understanding the electrostatic force and the way that it works that like charges repel. Okay, but what actually happened was different, all right? And that brings me to this simulation. So here we have gold foil, all right? And what we're going to do is we're going to fire alpha particles. And what this is right here is the platform they're being fired into magnified, all right? So we have a big view of everything inside this platform right in here, all right, down to the individual atom, all right? And what you can see actually is what he discovered, all right? So if I fire this, we'll get a taste. Oh, I think I need to reset it. There we go. Okay, so these are the alpha particles in purple. And as you look through it, you see that most of them are passing right through that gold foil. I'll give you a few reasons, all right? Alpha particles are tiny, all right? They are as tiny or maybe even tinier than atoms, all right? Now, we can see from the legend that those gold dots in the picture, those are the nuclei of the gold atoms, all right? So for the most part, those alpha particles are passing right through. Now notice what happens when many of them get close to a nucleus, like right over here, all right? They're starting to veer away unless they are fired dead on with enough force, okay? Then because of the electrostatic force, because a nucleus is net positive in charge and all of the negative charges are on the outside, very few of the alpha particles will have sufficient energy to continue and travel and hit the nucleus, all right? So what Rutherford discovered is that the alpha particles mostly pass through the gold foil. Why is this important? Because now we have this understanding that atoms are mostly made up of empty space. Now, this is hard to believe with the naked eye. If I look around me, what I see is that it seems like objects are fully formed. I can't look into an object and see mostly empty space, but the reason why is because this is zoomed in so incredibly close, all right? Much closer than my eye is capable of perceiving, all right? So we are down at this scale, all right, 6 times 10 to the negative 10th meters, all right? If you think about it, 10 to the negative 2 meters, that's a centimeter, which is about this big. I have to go 8 times smaller, all right, before I'm able to see things on this level. No wonder I can't see that atoms are mostly made up of empty space. And yet, because of what I discussed in previous videos about the strong force, these particles are able to hold together, all right? Not only are the subatomic particles inside an atom able to hold together, but clumps of atoms that make up the particles that are objects are able to hold together despite the fact that they're being gravitationally pulled and there is electrostatic force repelling protons from each other, most importantly, because the strong force is much stronger than the electrostatic force repelling like charges. All right, quick review of the 4 fundamental forces, along with our idea that atoms are indeed composed of empty space and the strong force is holding particles together. Now, the problem with Rutherford's model is that he reasoned that based on a previous theory about the way that electrons behave, that they would give off electromagnetic radiation as they revolved around the atom. And because they gave that off, eventually they would lose energy and they would collapse inwards towards the atom. This was no good because this proved, or seemed to prove, that all atoms were unstable and would eventually collapse in on themselves. How could that be? I'm looking around my house, I see nothing collapsing in on itself. I see most things seem to be completely stable and working fine. Well, the key here, the key observation that Bohr made to develop this model was to say, wait a minute, there is an electrostatic force pulling inward, but it is countered by a centripetal force pushing outward along the circle. Okay, so if we remember, I'm gonna label this in a different color. If we remember centripetal forces, all right, that's a combination of mass and velocity traveling in a circle, which means that the object is accelerating. Okay, I'm gonna continue to label these in red, all right? There is still a tension of electrostatic force pulling inward the entire time because out here we have negatively charged particles and in here we have positively charged protons, all right? So there's an attraction between these two things. The nucleus is obviously the most massive. It is far more massive than an electron, all right? Because it's composed of protons and neutrons, both of which, if you look at your reference table, are far more massive than electrons. So he reasoned that there is a strong enough centripetal force from the velocity of these electrons that they are able to travel in discrete orbits like this one, and this one, and so on and so forth, outside of the atom, all right? Now, as we travel ever farther and farther out, because of the great distance given, of course, it looks like nothing to us, because we're talking about 10 to the negative 10th meters, but as we get out there, there is a weaker and weaker pull between the nucleus and those electrons. Thus, we understand a little bit better how electrons can be peeled off, all right, if there is a low electronegativity to the element, all right? So between Rutherford and Bohr, we have many startling, important conclusions that are going to lay the groundwork for the future work that we do studying the atom, studying radioactivity, and studying modern physics. Just to summarize one more time, Rutherford did the gold foil experiment. He discovered that the atom is mostly made up of empty space. We have the strong force to thank for trumping the electrostatic force and ensuring that atoms don't collapse on themselves or explode apart because they're repelling like charges inside the nucleus. All right. Then on top of that, Bohr came along and said, well, wait a minute. No, number one, electrons are not giving out electromagnetic radiation. What we have is them traveling in discrete orbits because the electrostatic force that is pulling them inward is equaled by the centripetal force that wants them to move outward, thus resulting in them orbiting at discrete locations away from the nucleus. We studied in the previous video the phenomenon of energizing an electron to get it to hop to a further energy level, but we realized also that electrons are stable in certain configurations depending on the element. So eventually that energy would be given off in the form of light and the electron would hop back down to an energy level closer to the nucleus. All of this is crucial. All this behavior is crucial for us to understand some of the aspects of modern physics that we're going to look at in the future. In closing, what you really want to do is try to break down some of these landmark experiments in the simplest terms possible in terms of what you already know, all right? And when possible, take a look at a visual. I love this one. I hope it's been helpful for you. And we're going to continue our journey. So even if you feel like today you didn't quite understand everything about modern physics that you wanted to understand, specifically why the Bohr model is so important, for now, let's just leave it at atoms are mostly empty space. The strong force holds them together and allows the nucleus not to implode. There's an electrostatic force pulling electrons towards the nucleus. There's a centripetal force allowing it to pull outward, resulting in an overall orbit around nuclei. And that was Bohr's great contribution to the model of the atom. I hope this has been helpful, and I will see you next time.